Dear student, you are welcome to our fourth class. We will discuss today about the wave oscillation. Now, firstly, you have to know what is simple harmonic motion. What is simple harmonic motion? Okay, let me consider uh, simple harmonic motion. This is a simple harmonic motion. This is the bob, and this is thread, and this bob just oscillates, oscillating to and fro, oscillating. Now, this is the equilibrium position, uh, and the gravity is mg. And at this position mg, now we split the gravity mg uh, by two perpendicular components. This component will be mg cos theta, and this component mg sin theta. This component mg cos sin theta, and this component mg cos theta. This mg cos theta is a component of mg, and mg sin theta is also a component of mg. Now, this mg cos theta and the tension of the thread, and mg cos theta, these are two equal and opposite. Therefore, T equal to mg cos theta. Now, mg sin theta actually back the bob to its equilibrium position. Okay, now we can mg sin theta. Now we can say that the applied force on the bob, we can write F equal to mg sin theta, and F equal to, we know, ma. Now here we can write mg sin theta is the resultant force or the applied force on the bob. So F equal to mg sin theta, but we know F equal to ma. Therefore, A equal to g sin theta. A equal to g sin theta. A acceleration of the bob, A equal to g sin theta. Suppose y is the displacement. Y is the displacement of the bob, and the direction, this is the direction. This direction and this direction actually opposite direction, and mg sin theta, when the displacement is increased, mg sin theta, that means theta also increased. theta increase means mg sin theta increased. That means the applied force F increased. So Y is increased. Y is increased. Therefore, mg sin theta. That means F also increased. F increase means Y proportional to acceleration increased. Y increased means acceleration increased. Therefore, we can write like this: acceleration is proportional to y, that is minus y, because here acceleration A represents the F force. Acceleration represents the force, because F equal to ma, m constant, therefore we can say that A actually represents the force. A represents the force. A proportional to minus y. A means mg sin theta. Mg sin theta means F. Therefore, if y increased, then mg sin theta means F, that is A, increase. Therefore, if y increase, then A will be increased. So the direction is opposite. For this reason, we write sign, minus sign. The minus sign arises because of opposite direction. Therefore, acceleration is proportional to minus y. So this is a simple harmonic motion. Now we find out the characteristics of simple harmonic motion. First, and the displacement is almost this is 4 degree. The displacement almost linear straight line, So firstly, the particle or the bob displaced in a straight line, and secondly, the acceleration A is proportional to its displacement y, and directed in a opposite direction, minus sign, opposite direction. This displacement y, but mg sin theta F, or acceleration A acts in a opposite direction, and the maximum displacement of the particle of the bob is the same on either side. The left side and the right side is same. These are the characteristics of simple harmonic motion. Now we uh, represents uh, the wave equation. The wave equation, you know already, in our midterm midterm duration, we discuss about the we discuss about the um, uh, we discuss about the uh, wave equation, and we know uh, this is the first particle, and uh, and the other particles. This is the first particle. The equation of first particle for displacing to and fro or up and down, and this is y equal to a sine theta. A sine theta. A y equal to a sine theta is the displacement equation of the first particle. But if p is other particles, another particle away from the first particle, x is the distance from the first particle to p particle. X is the distance, and y is the displacement of p particle. Then y equal to a sine theta plus 2 pi by lambda x. This will be the equation of p particle. Now 2 pi by lambda x. 2 pi by lambda x, here this is the equation for p particle, and actually this is the general equation for all particles including the first particle. Suppose for first particle x will be 0, then this will be 2 pi by lambda x will be 0, then you will get y equal to a sine theta. This is the first particle equation you will get. Okay, now y equal to a sine, we can write theta as a omega t plus 2 pi by lambda x. Actually, the first particle and this particle, this is a complete wave. For complete wave we will get lambda. For complete wave the phase angle will be 2 pi. The phase angle will be 2 pi. Then for unit distance, lambda distance, the phase difference 2 pi. For a unit distance 2 pi by lambda, then for x distance 2 pi by lambda x. This is actually this one, 2 pi by lambda x. Now uh, uh, omega equal to theta by t or 2 pi by t omega equal to 2 pi uh, 2 pi 1 by t means f frequency, and 2 pi frequency. We know v equal to f lambda, then f equal to v by lambda. then omega equal to 2 pi v by lambda. Okay, now here we put this value of 2 pi v by lambda, 2 pi v by lambda. Now you can come on 2 pi by lambda, 2 pi by lambda outside of this equation, then y equal to a sine 2 pi by lambda, then 2 pi by lambda vt plus x. So we can write you can write this equation as like this equation. This is actually the representation of the wave equation in different form. Now we going to find out the differential equation of simple harmonic motion. The differential equation, just we going to establish the differential equation of motion of a body executing simple harmonic motion. We know F that is, we know from the characteristics of simple harmonic motion, A proportional to minus y, that is actually F. So therefore F also proportional to minus y, then F equal to minus ky. We can write this F equal to minus ky. So we know F equal to minus ky, F equal to ma equal to minus ky, ma means d square y by dt square equal to minus ky. A acceleration, then you can write d square y by dt square, acceleration. Okay, then d square y by dt square equal to minus k by m y. Just put this m to right hand side. Then d square y by dt square plus k by m y equal to 0. Now suppose y equal to a sine omega t plus phi. We got this equation. Here phi means 2 pi by lambda x. Phi means 2 pi by lambda x. So we know this equation. This is the wave equation, the displacement equation. We also call this the displacement equation, y equal to s sine omega t plus phi. Now we differentiate this equation, dy by dt equal to a cos omega t plus phi, and again d by dt omega t plus phi. Therefore finally we got cos omega t plus phi into, from this equation we will got only omega. It is a omega cos omega t plus phi dy by dt equal to a omega cos d omega by d phi. Now that means dy by dt. Now we differentiate this equation one more times, so then this will be du square y by dt square equal to a omega cos, therefore minus sine omega t plus phi, we will got another omega, and this will be omega square. Now minus omega square a sine omega t plus phi, and minus omega square, and this is actually y. This is actually y. A sine omega t plus phi, a sine omega t plus phi, this is y. So d square y by dt square. So therefore if we lift this term to the left hand side, then we will get plus equal to 0. This is the similar equation that we got just sometimes before. Therefore actually we have two conclusions through this derivation. We have two conclusions. One is the d square y by dt square plus omega square y equal to 0. This is the differential equation. This is the differential equation. This is our required differential equation of motion of a body executing simple harmonic motion. And the other conclusion is y equal to s sine omega t plus phi. This is the solution of this equation. Solution of this equation. First conclusion is this is the differential equation that we found from this derivation. This is the differential equation of simple harmonic motion, and y equal to s sine omega t plus phi. This is the solution of this differential equation. Now we are going to discuss about the time period of a spring mass system. Spring mass system. this is the initial length of a spring L. L is the initial length of the spring uh, without any load, and after loading the extension of this spring is del L. Del L. Del L is the extension of the spring after loading mg. Therefore, uh, the force the force force uh, the force here, the force F equal to K del L. From the characteristics of simple harmonic motion, we got A proportional to Y. A proportional to Y, that is minus Y. That means F proportional to minus Y, F equal to minus Ky. Similarly, here Y is the displacement. Here del L is the displacement. Then Y, we can write del L, and this is K. And you can write, put the minus sign. K del L, F equal to K del L, and this K del L must be equal to mg. Now this is without load, and this is after loading, and here this is the other equilibrium position. This is an equilibrium position, and this is after loading. This is also an equilibrium position. Now, if the body is now displaced from its equilibrium position and released, the body also displaced by the amount of y. Y is the final displacement of the body, and then you release the body. Then the body will oscillate up and down. The body will oscillate up and down along the vertical direction. Now here suppose at this position means the final displacement, the longest displacement here is y, and at this position the longest displacement, and at this position at this moment, at this position, F will be K del L plus Y. Del L plus Y. F will be del L plus Y. Here F equal to K del L, but here at this position F must be K del L plus Y. Del L plus Y. Here F must be K del L plus Y, and at this position, and the gravity also only mg, as it is before. The gravity was mg, now the gravity also mg at this position. Now at this position, the upward force exerted by the spring, F equal to K del L plus Y, and the downward force is mg. Therefore, the resultant force at this position, the resultant force, the upward force is K del L plus Y and the downward force is mg. Therefore, the resultant force at this moment, at this position, the resultant force applied on this body is F equal to mg minus K del L plus Y. This is the resultant force at this moment, at this position. The resultant force is mg minus K del L plus Y. So F equal to mg minus K del L minus Ky. But we know K del L equal to mg. K del L equal to mg minus Ky. Then we will get mg chole minus Ky. Y equal to minus Ky. F equal to minus Ky. F equal to minus Ky. But we know F equal to minus Ky. Now similarly, F equal to ma equal to minus Ky, ma d square y by dt square equal to minus Ky. Now if m just left hand side equal to 0. This is the equation. We have got this equation, and this is the equation that we found the previous section. We found this is the differential equation of simple harmonic motion. This is the similar equation. This is the same equation we have got now as a differential equation of simple harmonic motion. So this is the simple harmonic motion. And d square y by dt square plus omega square y equal to 0, omega square y equal to 0, and this is the differential equation, and this is also the differential equation of simple harmonic motion, where k by m is equal to omega square and k by m is similar. Omega square equal to k by m, omega square equal to k by m. So this is the same equation at different forms, but both are the differential equation of simple harmonic motion. So in this equation we have got this equation from this spring mass system. From this spring mass system we have got this differential equation, and this is very similar of the differential equation, very similar or same as the differential equation. So we can say that the mass spring system executes simple harmonic motion, because the equation we have got, this is for the simple harmonic motion. So the mass spring system executes simple harmonic motion. from this equation we can write omega square equal to k by m. Omega square equal to k by m. I am just recalling you that when we derived the simple differential equation of simple harmonic motion, then we consider y equal to a sine omega t plus phi. Then we differentiate 2 times of this equation, then we got this equation. We differentiate this y equal to s sin omega t plus phi, this equation 2 times. Then we got this equation, and this is the differential equation of simple harmonic motion. And instead omega square k by m y d square y by dt square plus k by m y equal to 0. This is also the differential equation of simple harmonic motion. Now finally here spring mass system, we got omega square equal to k by m and omega equal to root over k by m. Now we know omega equal to theta by t. If theta equal to 2 pi radian, this will be capital T. Capital T means time period. The time required for one complete oscillation. This is the time period T. 2 pi if for a complete oscillation the phase difference is 2 pi, the angle is 2 pi, then theta will be 2 pi and t will be capital T, that is time period. And t equal to 2 pi by omega and omega equal to root over k by m. Then we can write 2 pi root over m by k. This is omega root over k by m. This is 1 by omega. It is root over m by k. So the time period t equal to 2 pi root over m by k. And this is our required time period, required equation for time period of oscillation of a mass spring system. A mass spring system, we have finally got the time period t equal to 2 pi root over m by k. This is our required equation.